Okay, so now we'll go into the show and tell portion of the show. Who has a robot that they would like to show? Give me a show of hands just so I can get a feel for how much time we need to allocate. Okay. Rohan, are you guys showing something today?
Yeah.
Okay. All right, so let's, who wants to go first and show the robot? Yes.
Is my laptop still up there?
Yes. Okay. Well, a laptop is here. I don't know if it's yours.
I'll be really quick.
Oh, it is.
Yeah. So, for most of you who were here last month, you remember MontBot. These are the ones that we're building. Nice, cheap robots. And this is just a quick video to remind you of what happened last time, where it's scanning, it's trying to find the object. And if you remember last time, I think it found the object and then committed suicide.
It's awesome. This video is amazing.
And what's amazing is that, it's going to go to do the next one.
We can't see it.
With only one line of code change. Oh, it's not? Oh. There we go. Let me play that again back. Back button. That's right. And where'd it go? Here we go. Oh, yeah. So basically, I was trying to show it off, and it did find the object, but it committed suicide. The good news is that with only one code change, one line code change, I was able to bring this to Robo Games and get the gold medal. And I'll scroll down and show you what the change was. My comments have been disabled.
Go back. Go back.
Oh, that's
Previous video.
It auto goes to the next video.
Yes, it does.
Yeah. So let's hit pause.
Chris, what company do you work for?
This is all my own. I actually.
No, I'm talking about what's up on the screen here.
What?
Baby learn safety.
You're a YouTuber.
Yes, I do work for YouTube, so I apologize for what's in my history. So the one line change that I found was at the top I had int kill all equal to robots, so it committed suicide. So the only change I did was change it to humans. So I was going to demonstrate it now, but somebody told me, well, maybe not. Anyways, we're going to be building MontBots again this weekend. If you want to get into either artificial intelligence or build your own tabletop robot for the challenge that's coming up in June, this is the guy to do it. They're really cheap, easy to make. You can build one in one afternoon. Come see me. That's it.
Thanks. Maybe we'll do a series of Robo Magellan here. Ralph, you can start us off.
Sure. That's Blackbeard. I was at Robo Magellan with him, and you guys have seen him before. I've tacked on a few more things. Actually, let me go on a second. Just added a little bit more hardware. I had to get a some kind of a bump sensor on here for touching the cone, and threw the Pixie Cam on, and some more LEDs. Because I could have LED envy from Marco's spot. He's got a lot of LEDs on his spot. So, and I put the siren on here, but I think I turned it back off. But so you can see a fair number of LEDs. Marco's got a lot of LEDs, so I wanted to kind of keep up with that. Anyway, and it was a lot of fun, and we had a blast doing it. I did not touch the final con. I was one of the 3 that started but didn't touch the com. That's okay. I learned a lot doing it. And all that. And I have some pictures here. I'm going to just show something here. Let me see. theoretically this will work. Here we go. Let's try this. There we go. So that's my my final approach path to the final cone. That's how close I got. But I found that the problem that I had was the Pixie cam's got about a 45-degree field of view on it, and I didn't start looking at the Pixie cam until the cone was just to my left, basically. And so I had missed it by then, and my code kept it going forward and looking, and so I'd already passed the cone. So that kind of talks to some of the things I learned, so that's important. What did I learn? One of the things I learned is GPS is really pretty wonky for this, right? It's a big circle error probable, right? It's a plus or minus 4 meters. So what I had done in my testing the day before was I found that I was looking at the camera too soon, 100 feet away. I'd lit up the camera and it was causing some issues. So I tried to wait a little longer until I got closer to the endpoint to turn on the camera, and I corrected too far. And you kind of split the difference. But GPS at the end of the day is kind of a blunt instrument for this event. And I ran into some other issues like on my, let me show you how you'll like this one. That's my first run, and the first run was the best one for me. The other one is my second and third runs weren't so great. And some of the stuff I ran into was...
Get the picture of dead Blackbeard?
Yeah, I got it in here somewhere. This got to come back out. Talk to me. But let's see if I can get this to come back out. Yeah, the other two runs weren't that great. So
I love the one where it hit the fence and fell over.
that was a good one. Here we go. Okay, let's see. So that's the route that I took, and I was trying to follow the green line to the final cone. I kind of swerved off to the right. I guess that's GPS plus the compass isn't super great. I found it on the bench in a quiet environment without my motors running. That compass is pretty accurate, but once I start driving around, I get a fair amount of compass drift, and so I swerved off a little bit. Got close, but the other thing I wanted to show you was this one.
Yeah.
That was the end of my third run. So what are you gonna do? Yeah, funny stuff. Anyway, we had a good time. So GPS is a little wonky. You got to deal with the inaccuracy of GPS. Magnetometer can be thrown off by who knows what. So, and then make sure you turn on your Pixie cam soon enough, or whatever your vision system is. Make sure you're not, not ignoring the camera as you approach your cones. And I'm going to look at some other things as a possibility in the future.
Don't unplug mine. Can you go back?
Oh.
After you're done, I want to just, so here. So just in case people don't know, the goal of Robo Magellan is to get from here autonomously over to a traffic cone, which was probably about here.
Right about there, yeah.
And along the way, there's 3 other cones which you can touch to help reduce your time. So it's a timed event from one point to the other autonomously. Most people who touched it probably did it. It takes maybe like 3 to 5 minutes, I would say. It's probably about average to go from there to there.
Marco ended up with like a 12-second game time, I think with 3 minutes and then 2.25 multiplier bonus cones. And then the silver, help me out here, who got silver?
Who got, it was a team, right? College team, wasn't it?
No,
They
were third, right?
they came in third.
I'd say Robley was third.
Regardless, there was one straight run.
Palo
The
Verde
third
or
place,
something.
the bronze medal got the straight run in 43 seconds.
That was fourth. Oh, third also?
Really?
Okay.
Because they had a time of like 40 seconds. That's a very fast straight run.
So, again, I think the best strategy in this game is go for a straight run your first time. Tag the gold cone and get that in the pocket, and then get fancy if you want to, touching bonus cones. But the bonus cones, if you want to medal, you probably need the bonus cone.
Yeah.
This time you definitely had to touch 2 bonus cones to
Well, I got the gold.
Yeah.
But again, the bronze medal, it was just a straight shot in 43 seconds.
Okay.
Yeah.
33. 32.
Oh, that's it.
I thought it was 32 seconds or something.
Yeah, interesting stuff. So one of the ideas I want to do to improve this in my next attempt is, since the compass in a quiet environment seems to be pretty accurate, when I turn on the motors it seems to get wonky, or when I'm not driving around it seems to get wonky. So I have a solar compass that I built for the NASA SRC last year. So I want to put that on here, calibrate that on power up to my magnetometer, which before I light the motors should be accurate, and then just use the solar compass for course after that. It's one of the things I want to try next time.
It's not raining.
Sorry?
As long as it's not raining.
Yeah, as long as you have a reasonable shadow, so that's the trick there. Anyway, that's pretty much it, thanks. Oh,
Quick question,
yeah.
has anybody tried to shield the motors with like the tinfoil hat?
Yeah,
I
don't know.
Move the compass as far away from the motors as I can,
Yeah.
and from the speakers in my case.
Okay.
Yeah.
You know, my odd little design here, kept getting taller. And at one time I had GPS down by the front by the camera, and I was getting plus or minus like 20 meters. And then I moved it up higher, and that got better. And when I put it farther from the electronics with the pill bottle, I got to most of the time within a couple meters. So GPS can actually be pretty good, but you have to do filtering, look at what satellites are in view, and watch out for the oddities that happen.
Yes. All right, yeah, good stuff. Another question?
The robocar races, I forget the name of the company now, but there was a company doing one of the laps, the track, with a full-size car doing nothing but differential GPS on a racetrack, and they were actually had one of the best times.
You know, the differential GPS can get a lot more accurate, right? My understanding, I guess. Like the Seattle rules for Robothon, I think they expressly forbid differential GPS.
Yeah, everything has to be on board the robot.
Yeah.
It was impressive to see, though. They were able to do a full-size car that way. It's completely cheating, but
it's nice. I like it. Very nice. Yeah. Okay.
So this was my entry for Robo Magellan. So you heard Ralph talk about the challenges of compasses and GPS. One way to get around those is just don't put them on the robot. So actually, I started kind of late building my robot compared to most, so I didn't have time to add a lot of sensors. So there's no GPS, there's no IMU compass of any kind, and there's no bump sensors. Actually, excluding all that stuff helped me focus on what I really needed to do to touch the cone, and that was really good at least for me. My strategy was really good wheel odometry. So you saw that picture that Ralph had put up on the screen. So while everybody else was getting out their GPS, I had one of those little wheels, that you measure distances with. So I had distances. I had set my own waypoints along the path, down to the centimeter. So I basically told my robot, go in that direction for 25 meters, turn 62 degrees, go 60 meters, turn 90 degrees, and look for the cone. And it turned out that was good enough to actually help me touch the cone. It wasn't good enough to find other cones along the way, so that's something that I'll work on for next year. But I've been watching this event for several years, and I've always seen people get tripped up by GPS. Not just at this course, but when we were out at where was it before?
San Mateo Fairgrounds.
Yeah. Robots start going in the completely wrong direction, and it's all because of problems with GPS. So I said, don't need it. Just point the robot, let it go. And the wheel odometry was good enough that I could get to points along the way.
Do you have any proximity detection?
So once I get to the cone, I have.
What was the question?
Sorry.
I was asking if you had any proximity detection.
There is one ultrasonic sensor, which I use to tell how far away I am from the cone, and that's how I try to touch the cone. It doesn't know it actually touched the cone, but it can infer that it touched it by knowing how far it was away a few seconds before, traveling essentially through the cone, and then stopping. So
you can't knock the cone over. You knew that.
Yes, but I did.
I know, it was a sweet question. Good run.
It's a fine balance.
Yeah.
So I started with I knew from the beginning that detecting the cone, if you can't detect the cone, it's like game over. So that's actually where I started with on the robot. So it has really good cone detection algorithm, and I knew that if I could get close to the cone, that it would be able to find the cone, and and be able to touch it. So I'm using this Pixie Cam, which is the same thing Ralph is using, and it's a really simple way of giving vision to a robot. It's basically a color blob detection device, and it outputs an X and Y coordinate, essentially. X, Y, and size. You get that over USB. So you don't have to do any fancy tricks with OpenCV. It's very little programming, and it's very effective. So that was one thing that helped me out a lot. If I
See if you can make it to the end.
well, if I tell it to go, you'll see that it goes. Okay, and now it just keeps going until, because ultrasonic doesn't work at short distances. It's good maybe down to a few inches. So once it gets to a few inches, it says, I must be on the right track. Let's just keep going. It counts the number of ticks on the wheel encoders and says, once I've gotten the proper number, plus a few extra, stop. And so that's what it does. So that was my entry for this year. Next year, I hope to add a few more of these other sensors. Not necessarily rely on them, because I think I've got a proven strategy. In fact, I think I could probably, based on the course we had this year, touch two more cones just with what I have here. If I had a little more time to do programming, no GPS. So we'll see. We'll see what happens for next year.
Without a compass, how do you do accurate turns?
So the question is, without a compass, how do you do accurate turns? So I did quite a bit of work to nail down the wheel encoders. So I know exactly how many ticks on the encoder will make the robot go a certain distance. So turning is just the same. When you turn, one wheel goes forward, one wheel goes back. So I know how many ticks it takes to go 360 degrees. And if I need to turn 60 degrees, I just divide that by 6. And it works surprisingly well. A lot of people have dismissed this kind of differential drive robot, as that'll never work, because you do get a lot of friction when you turn. But all four wheels are independently driven. They all have encoders. So I can do averaging on the left and right side, because I've got 2 encoders on each side, which helps reduce the effects of slipping. If one wheel slips, it doesn't matter, because I've got the encoder from another wheel. I can do averaging. I can get speed very accurate, and distance very accurate too. Yes?
Well, then I assume that when you start the robot pointing in the right direction, how do you accurately, because if you're off a couple degrees, 300 meters out, you could be way off.
That's very true. So fortunately, they give you 3 tries for this competition. So for the first try, I had pointed it a little bit to the left on the first leg. So I had 3 legs, and then by the second leg, it was going off into a garbage can. And so I had no obstacle detection, so I just had to kill it. Second time, I was able to get close enough to the cone, but for some reason, my Raspberry Pi died right when it got to the cone, and all it did was just sit and spin in a circle. So that's what happened that one time. I don't know if we were talking about that, but just sat and spin in a circle, and it couldn't find the cone. The last time I got close enough to the cone, then everything worked, and
That was a nice run.
yes.
That's a nice picture of a cone. I was thinking it'd make a great T-shirt.
people have suggested that. I'm not that mean. Okay, who else? The question is, how did I manage not knocking it over? Well, when you're a certain distance away, say, a foot, I know I'm a foot away. I know how many times the wheels should turn to move it a foot. So I just move the wheels that number of times, assuming that I'm going in the right direction. Then I move just a little bit more in case the wheel slipped, push into the cone.
And then back up.
No, I just stayed there. Okay.
That's handy. Okay, hi. So you guys know us. We're Team Victoria. Mike couldn't be here today because where's the camera? Mike couldn't be here today because he broke his ankle trying to save a small child. He was definitely not chasing squirrels.
Did he successfully save the child or unsuccessfully?
Yes, he successfully saved the child from a burning building and was chasing no squirrels when he broke his ankle.
I think it was an orphanage.
Yeah.
An orphanage. One of those stories. Okay. So in the same theme of the evening, we're sharing our experience with Robo Magellan. So we were able to, on our first run, touch the goal cone, and on our subsequent runs, not touch the goal cones. But we'll talk a little bit more about that. The path that we had planned out that touched the goal cone took us out of the tree cover as fast as possible. So we'd started in the same place everyone else did. We'd gone back, we'd gone here, forward, there, and then after there, we went up to here and turned. So in our strategy, we actually laid out a whole bunch of intermediate waypoints for the robot to get to because we didn't have any obstacle detection working. We have all these fancy things like LiDARs and depth cameras, and we didn't use any of them. Yeah. So it was a big enough scramble trying to get the last minute everything else to work. I'll just put this video on of our first run while I keep talking. So to echo people's comments about IMUs with the lesson learned, we actually had the exact same experience. We had a LSM 303 something with something else that we'd gotten from Adafruit, which was just a Excel mag gyro, and we had all the same problems with drift, and etc. And whatever packages that we had from Ross didn't really help too much in the short amount of time that we had to try to tune them. So we just kind of ditched that and we bought something better.
Tuning them didn't look not very great.
We tried to tune them, it wasn't working well enough, so we ended up just buying something that I think we would all recommend highly, the BN055 from Bosch. Yeah, Mark.
Did you have an agreement with the guy in the orange shirt to stay behind you?
He's one of our teammates.
He's actually our teammate.
Yeah.
Not a worn hat shirt.
While we were doing testing, he drew.
It's for wandering around with the other people.
Yeah, there you go, Mark.
I think every weekend we worked, he came up in his orange shirt. So
especially when we were testing the cone detector.
That's very hard in testing, we know.
Yeah. So $40. You can get it at Adafruit. It'll give you a full quaternion or Euler angles, and it's continuously calibrating, which is wonderful because it does really well at telling you which way is west, unless you think that it's telling you east, and so then you end up spending almost a whole day trying to figure that part out.
But once we figured out how to calibrate it, until we drove over the metal grate.
Right, and then it becomes uncalibrated because it's always trying to recalibrate. But anyway, highly recommended part. It doesn't really seem to drift. Doesn't throughout our runs, and we did close to a dozen different runs in this environment. We didn't really see any problems with the compass or the whole IMU. So I'd highly recommend it to anyone who's interested in paying a little extra money. Mark was able to get it running, in an evening?
Yeah, well, it hooks into I2C. They got the libraries for it. You can get it up and going really quick.
Yeah.
It just took us a while to figure out the calibration.
Right. So if anybody saw Mark doing a little dance with the robot, that's why, because he was calibrating the IMU. Let me see. What else? Apparently GPS likes to be pointed up. That doesn't seem to matter in the field, but when you're close to things, it gives you like a 9 dB advantage. Our odometry was not as good as Osmond's, so we tried to rely on it, but we were unable to. What else? Make sure you test your cone calibration at different ranges. So when we went to our third run, when we would have seen the cone, and actually our cone detector if you looked at the nice outline of what it gave you, did in fact see the cone, it still said no. So make sure you do lots of those testing. Our second run, the problem that we had is the robot just kind of locked up, if anyone remembers. Make sure you test your fail cases, because our fail case was untested. We fixed it for the third one. But you know, had we not, maybe we would have gotten a better score. Mark, anything else to share?
Testing is key. I mean, yeah, the day before we were at the fairgrounds and just trying to do as many tests and as many runs and try things out as much as possible.
Yeah. And anyone who's interested in the R200 camera that's in here, apparently it throws off enough other EM noise that it will keep you from getting a GPS lock. So all the time we would try to test it because the GPS was mounted down here and I wouldn't be able to get a GPS lock and there would be no clouds and it was the most frustrating thing ever. And then we just moved it a little bit and then it would come up instantly. So it's most likely because, you know, it's an active camera. So that's probably why it would throw off that sort of noise. But if you're not thinking about that, you might not. You might waste a week. Yeah. Anyone? Yeah, Mark.
Can you repeat the magnetic sensor? It's one of those BN01.
BN0055.
Yeah. Sorry, there's an extra O in there.
It's by Bosch.
Yeah, but we got the Adafruit one. The the board that Adafruit makes.
Yeah, they
put it on.
They have a breakout, but it's the BN0055 chip.
Yeah.
What was the camera again?
So we're using a RealSense, an Intel RealSense R200.
Oh, okay.
Yeah, because we wanted to take the depth data and use it for obstacle avoidance, but we did none of that, and we just used it for the fact that it has a color camera. Anybody else? Yes? No? Good. Oh, yeah.
How did that work? I mean, were you able to get depth data from outside?
Yeah. So, settings-wise, we play the next one. Settings-wise, you actually, so what we found out from that is that so in case anyone doesn't know about the R200, it's got one color camera and it has two stereo IR only cameras, and it tries to take the two stereo images and make, right? Okay. But by default, it also has a little IR projector that projects a pattern, so it kind of does a little bit of structured light as well. And in indoors, that's absolutely necessary. There isn't actually that much light in here. But outdoors, that's still on. It doesn't know the difference, and all of its pattern gets washed out. So outdoors, it was completely sun blind until we realized you could shut that off. And as soon as you shut it off, everything just came up. So you'd be able, so in this scene, you'd be able to see all of those bushes if you wanted to. You'd see the grass, you'd see the...
all that 3D point cloud data as if it was structured lighting that are outside of the stereo.
Because it's inherently stereo, the structured light stuff that they add to it, I'm guessing, all I did was I found the setting, I shut it off, but yeah. I would guess to say that it's just so that there's more features for the stereo vision to pick up on, as opposed to doing a real structured light thing where it would figure the geometry based on the pattern. Yeah.
Okay, cool.
Anyone else? No? So this was our third run.
We missed the first bonus cone, we got the second bonus cone.
Yeah, second bonus cone being over there. So, unless there's any other...
We're gonna keep going.
Yeah, so, yeah, we're gonna keep going. We'll probably bring another version of her to June competitions around here, just run it outside, and we're gonna try to go up to Seattle in September, just so that we keep our momentum.
Right, where the waterproofing will probably come in handy.
Yeah.
There was the weekend before, we were testing her. She sat out in the rain all weekend, just getting rained on as we were testing her and everything else. It was pretty cool.
Yeah, actually, there's a picture of that here. So, I don't know if that's convincing enough to people, but yeah, she only had one leak, and it was here. and it was static, and there was a little container, so a little bit of caulk, that was it. So, the lawnmower chassis did as well. Yeah, it wasn't torrential rain, it's just kind of annoying sort of rain, but something that you would be nervous of.
Will you be able to speed up the wheels?
Yes, we will be getting new motors. We were very conservative this year. We got the torquiest thing that I thought was reasonable. And apparently that was so.
If they hadn't cut the grass, there'd be a different set of winners.
Yeah. Yeah. So we did a lot of testing in the lawn behind the building where the grass wasn't trimmed, and she didn't care at all. The only thing that she cared about was moving slowly in the grass, but we have to work on our controllers for that. We have an excess of torque. Each motor shaft right now can do 2,000 ounce-inches. I don't know, just to refresh people's memory if I hadn't mentioned it before, during construction and testing, the most popular failure mode was for me to rip the steel shaft adapters from between the wheel hub and the motor shaft. So we probably don't need quite that much torque. Yeah, I was writing. That's a mistake. I need to lose weight. Anybody else? Yeah.
You track down the source of your somewhat serpentine movement versus having a smoother.
It's Mike's code. No, I make that sound like a joke, but so our realistic plan is to be using the robot localization package and move base and obstacle avoidance and all that. But as we were running out of time, Mike had been already starting his strategy module, which he talks about so fondly, which is what we used this whole time. And for that, the navigation code was simply, am I off bearing? Stop, turn. Am I on bearing? Good, go straight. So we've since discussed smoothing that out before we
basically
make the
key
switch.
part of PIT.
Well, the fact that there was no going straight while you turned, it was just those two lines.
And apparently it's been smoothed out, but we haven't had a chance to test it.
Yeah, because somebody's chasing squirrels. I mean, saving children. Okay?
Today we're going to show a Kamigami robot that we made together. We built it using some parts we got from a kit. Here's a demo of it.
Yeah, it's on.
It works better on carpet.
Well, here's an opportunity. Oh wait, we can just we're going to experiment. You can drop it from a 2-story building. Is that one of those dash robots? Yes, it is. Okay, well, shorter than the 2-story.
Go over there so we can get on the camera. Yeah, under the table. There we go.
Now we get into this. This is modeled after a cockroach. It starts off with a flat piece of paper. You just fold it into shape and use little plastic rivets. And you need really small fingers, and she's really good at this. And she put it together after the last meeting. Very nice. Anybody else?
What does your screen look like?
Oh, yeah.
Zoom in on that. So what is that? Is this a trackball or something?
It's like a joystick, isn't it?
Yeah.
It's a virtual joystick.
Cool.
we're working on, but we're more interested in just getting the data to and from the device and showing it for you.
Okay.
So everything's TLS encrypted, and eventually it will actually be end-to-end encrypted as well. So you have public-private key crypto. I think I had a question over here.
Yeah, so you're using Rossbridge for the communication from the robot to the cloud?
We're compatible with the Rosebridge protocol, but Rosebridge doesn't scale in the cloud. Okay. So we had to write a proprietary solution to be able to scale up to torrential amounts of data up in the cloud. Yeah. So essentially only the authorization system, we had to break the protocol there in order to be able to support all of the end-to-end crypto that we want to be able to do.
So it's kind of like RViz in the cloud?
Yeah, it absolutely enables RViz in the cloud. Yeah, and so some of the other things that we're thinking about are being able to run, just spin up Gazebo instances in the cloud for you, so you don't have to set it up. So if you're doing like a class or something, you can have your students simply developing things in the browser or on GitHub, and then uploading it to the cloud, pushing simulate on our web interface, and you'll upload your world files and your robot descriptions, and we'll run the various instances, as many instances as you want. So that way you don't have to have all your students install Linux and install ROS and can learn how to configure all of those things. You can go straight to robot programming with none of that stuff that tends to prevent people from getting started.
You need to get this guy to do a presentation.
Yeah.
Actually, got a question that Yanni just discovered us. If you're also aware, there's a Silicon Valley ROS users group.
Oh no, I had no idea.
So we can hook up later and get you hooked up with their meetings as well.
Yeah, that'd be great.
Okay. I'm sure they'd love to hear that.
Awesome.
Like the robot pose is significantly less noisy because in order to get a good localization off one marker, you need to have a very, very high contrast between the black and the white sections, and poor lighting doesn't really give you that. But when you have multiple markers, that we're able to smartly combine the estimates from each one in order to get a final pose of the robot.
Yeah. So you're getting XYZ position and orientation quaternions from one fiducial?
Yeah, from each fiducial. And the only requirement that we place on fiducials is that the fiducial itself is flat. It's not like flopping around. But other than that, you can place fiducials wherever you want as long as the camera can see them. So you can have fiducials on your wall, your ceiling, the floor, depending on how many fiducials you want.
Anywhere you want.
Yeah.
Could you define fiducial, please?
Okay.
A fiducial is a marker that is reasonably fixed in space. So you see we've got these fiducials here, right? Now, the way the algorithm works, so that's a fiducial, for example. Right there. It's any marker that the robot can recognize. And is reasonably fixed in space. As a practical matter, however, we can actually move the fiducials, and then the robot will remap the fiducial location and will update the location in the map, as long as it can see more than one fiducial at a time. So, it's constantly doing simultaneous location and mapping of the fiducial space.
So just to be clear, you need 2 fiducials at a time in order to do the mapping. But for example, if you go up towards the edge of your map, you can still get localization as long as you see 1.
Okay, any questions? Great, thanks very much.
Oh, wait.
I just have a note, because we were hoping to demonstrate voice protocol. Not quite there yet, but we almost had it working Saturday, and the first time we gave the command to go to goal, the robot basically said, "Sorry, Dave, I can't do that." And the reason it said that is because we made a little mistake in our mathematics, and the robot couldn't orient itself. It couldn't change its pitch to be flat to the fiducial. So it actually gave us an answer that we understood what exactly was happening. Easy to fix it.
So, so that's actually the other disadvantage of doing it in 6 degrees of freedom, is that sometimes the robot pose that it outputs is kind of like at an angle. If the ceiling isn't perfectly flat and it assumes that you're saying that you have a flat ceiling, and basically the robot will always be at an angle in RViz, and that'll make it difficult for MoveBase to try and get the robot at an angle when you have a differential drive.
Tony.
Yeah, with the continuous slam, do we see drift of the fiducials as a whole, like that network of fiducials to migrate? If one of them 0, 0, the whole network is migrate.
So we assume that the first fiducial that you see is fixed in space. So the first fiducial that you see when you turn on the robot is fixed in space, and all of the other fiducials move around that fiducial. So it is possible that there is, you're absolutely right, the SLAM algorithm can cause drift in the markers, but at least in principle. But because you have an origin fiducial that doesn't permit infinite movement, as long as you continuously map, at least in principle, the map should get better and better.
I was going to ask. So, you say you're doing localization, but you're not filtering the pose so it doesn't jump around as much.
So right now this is the unfiltered output.
Right, it's just the geometry.
Yeah. So this is without odometry. This is without an extended Kalman filter.
Right.
Right now this is I think what we were seeing earlier is up to 20 centimeters approximately of variance in better lighting conditions where the fiducials are pretty well lit. Like you can see that in the corner that it's very difficult to see. So like if you're in an office environment or something like that where you have fluorescent lighting that's pretty bright, you can get way less noise.
Okay.
Oh,
yeah.
One more.
What happens if you have a large area with a lot of fiducials? Do the fiducials have to be a particular uniqueness?
So each fiducial is associated with a number. So, and there's various dictionaries that Aruko provides. Right now we only support one of them, which has 1,000 markers built into it, but there are larger dictionaries. And basically you can also print larger and larger fiducials that have more information. Like these are, I think, 8 by 8 pixels, and you can go up to like 12 by 12, which gets you a lot more information. But they do have to be unique within each environment. Yeah.
What if you lose your origin of your fiducial in the beginning, the one that your camera first sees? What happens if the angle is either too much, or you just completely lose your first one after you've already started?
After you've already started, what we do is that one's assumed to not move, and if that one kind of disappears off the map, the other ones will still. Then you might see drift of the entire map move around that one origin that no longer exists, but we have not done testing of the origin fiducial disappearing.
Right. So you don't. If the origin goes, the rest of the data is still in the map. And it will continue to do SLAM, and to Tony's point, it could drift. You could fix another one, yeah.
Yeah, you can. I think we have some. Do we have the tool written? I don't know if we have it written yet, but there's a tool that we were going to write that lets you change the origin fiducial. So if you want to make it a different fiducial, it'll move all the map data over, like change all the transforms so that the whatever fiducial you specify is now at 0, 0.
Okay,
thanks.
Thanks very much.
This will be very quick. This is my robot. I call it Nino. My name is Steve. So right now, I have a motor controller, and I have a LDS, and I have a RealSense R200. So far, I think the odometry is pretty good. It's very accurate, and the G mapping running on the ROS. So the G mapping, I can get a very good mapping of my home, about 2,000 square feet. So, and the next thing I'm working on is the voice control, and also plus the vision. For example, I want to make sure that later it can recognize my kid's face and wake him up. That's my next target. And yeah, that's basically will keep me busy for some time.
So is it an indoor robot or is
It's
it outdoor?
indoor. It's indoor. Yes.
Looks like about the right size for a Roman Magellan. You might want to think of that.
No, I don't want to do that. I'm more interested in wake up my kid.
Indecorel.
So you have seen this robot before, and it actually didn't change much since the presentation in January. But if I can get one picture up on the screen, let's see if that works. I can talk a little bit about GPS. I need an ETA.
The robot has a badge. It's not his badge.
That's actually the tracks of my 3 GPS receivers of my final run. And you can basically see how far they are apart at different points. And 2 of them are actually the same chipset, and they are still basically the blue one and the yellow one. They are the same U-Blocks Neo M8 N chips. The red, or actually the green underneath, is attempt to do differential GPS with another base station, which was sitting on top of my car in the parking lot. And that worked pretty well, except one time I hit the tree audio. So that's about it. If somebody has questions about the robot afterwards, it's here to look at or whatever. Thanks.
All right, so we'll take a 10-minute break. We'll take a 10-minute break. It's 8:20 right now. At 8:30, we'll meet back here, and Al will start the presentation.